We've begun to work with and understand exponential functions. Let's look at how to solve them. And just for fun, let me give you some actual problems we're going to solve in the next few minutes. How about 7 to the x? So there's an exponential function equals 7 cubed. So what do you do when you're solving an equation? You're trying to see what x equals. How about 6? The exponent here is x plus 6 equals 6 to the 3x minus 4. Once again, solving for x. How about 3 to the 5x minus 8 equals 9 to the x plus 2. And then one last one. I mean, we'll do more than probably just this, but I don't want to forget this one. Actually, I should put in a e to the x squared, e to the 9th here. 4 to the x equals 7. These are all equations with exponential functions. In each of these, you have an exponent. We have a variable in the exponent. Now we're going to try and solve these. And if you think about it, when you first learned to do algebra, you had a problem like this. And you were asked to solve for x, and you learned, well, the key is to get x by itself on one side, and you realize that, okay, if I divide both sides by 7, x equals 3, there's your solution. And even it's something like this. Trinomial quadratic equation, x squared plus 6x plus 8. Ends up we can't use the same rules we used here, but then we learned to factor. And factor is one of the ways we can solve this. So if we factored this, x plus 2 times x squared equals 0, and then when we solve it, so here are our solutions. Turns out there's two solutions. But let's look at this first equation. I'm trying to solve for x, but it's almost like, I like to say, I got a problem. I'm trying to solve for x. I'm trying to rearrange this equation, move things around, do things to get x by itself on one side. But you know what? Right now my x is like stuck up here, like in the exponent. I can't even, it's like I can't even get at it. I somehow need to sort of like bring this x out of the exponent to where I can get at it, where I can solve for it. Well, that's all true. Now what we're going to see right now, there are actually two main methods to solve equations that have exponential functions. And the first one, which we're going to do right now in a few minutes, I'm going to call it same base, and once we look at it, you'll understand why I say that. And the second method, which we're not going to do actually for another lesson or two, because we have to learn some more stuff. Maybe some of you have had logs before, or what we call logarithmic functions. That's the other way we're going to use to solve some of these equations with exponential functions. But for this lesson, we're going to strictly look at solving equations where we can use the same base method. A lot of times you can't use the same best method, so you end up having to use logs. But there are going to be problems where we can use the same base method. So it's a pretty simple principle. Matter of fact, let's start with this first equation. Now maybe a lot of you already thought this as I've talked about it, and you've already solved this in your head, but the solution for this equation, I always like to say, the solution for this equation is the value of x that makes this equation true. Well, what number, hopefully, obviously you see what number would x have to be for this equation to be true? 3, right? 7 to the x equals 7 to the third. For that equation to be true, obviously x has to be 3. But what's the key? The whole key is you have two exponential functions on each side and they have the same base. When you have two exponential functions equal to each other and they have the same base, you can simply set the exponents equal to each other. Here's the second example, a little more complicated. We're asked to solve this equation. 6 to the x plus 6 equals 6 to 3x minus 4. Well, first thing I notice is I have the same base. 6 and 6. If you have two exponential functions equal to each other with the same base, then you know the exponents have to equal each other. So I can just set the exponents equal to each other, and then I can solve this equation. And this is just like a normal linear equation. Subtract x from both sides. Add 4 to both sides. Looks like my solution is x equals 5. And like always, once you solve an equation, you can go back and check. So if I plug in 5 for x, left-hand side is 6 to the 5 plus 6. Right-hand side is 6 to the 15 minus 4. Looks like 6 to the 11th times 6 to the 11th. So that checks out. All right, not very complicated. If you have two exponential functions equal to each other and they have the same base, you could just set the exponents equal to each other and solve. Now let's look at this third problem I have up here. Now that we're learning how to solve these kinds of equations, let's look at how we would solve this one. Three to the 5x minus 8 equals 9 to the x plus 2. So I notice, okay, I have some exponential functions. Now the first thing I'm going to try and look at, because it's usually easiest, is do I have the same base? On the left-hand side, the base is 3. Right-hand side, the base is 9. So at first blush, first glance, it's like, no, they're not the same base. But then you ask a secondary question. If initially they're not the same base, then ask yourself, is there any way I can do some manipulating and get them to be the same base? In other words, what I'm thinking here is, I realize that 9 is 3 squared. So let's go in here and let's replace this 9 with 3 squared. So I have 3 to the 5x minus 8. So 9 is 3 squared. So So it's almost like 3 squared raised to the x plus 2 power. Now here's where you have to remember some of your exponent rules. What do? So inside here I have an exponent 3 squared raised to another exponent. What do you do when you have one exponent raised to another exponent? Well, you multiply, right? So just to make it very clear, you'd have 3 equals 2 times x plus 2. So now, look what I've done. When the problem began, I did not have the same base, but then I realized, since they had made the base up here 9, I could change it, and now I would end up with the same base. So now if the base on both sides is 3, I can just set the exponents equal to each other. Now I can solve this for x. Subtract 2x from both sides, add 8 to both sides. If I didn't make mistakes, my solution is x equals 4. I can check real quick. Let's go back and check right here. If I plug in a 4, that's like 3 to the 12th. Plug in a 4 here, that's 3 to the 12th. So it looks like that's correct. All right. How about, let's do maybe one more. Well, let's do a couple more actually. There are a few twists that you face sometimes that can be sort of confusing if you haven't done any of these yet. So here we go, 1/5. That whole fraction raised to the x exponent equals 1/25. If you want to, you can think of it as 1/25 to the first power. So if you think about these like two exponents with two bases, I've got a base of 1/5 and a base of 1/25. Not a whole lot I can do. Then once again, you realize that 25 is 5 squared, so you say, well, hey, whoops. Oh my. That was just to throw you guys off. And furthermore, hopefully you see that 1/5 whole thing squared is the same as this, because the 2 gets applied to the top and the bottom, and 1 squared is just 1. So then now look what we have. We actually have the same base. And this one's really easy to solve. So you may see problems like that. How about, let me do 2 more of this type, and then we'll do a few story problems. I want to do, let me look it up. I thought I wrote it down, but I did not. This is just a little tricky. Let me find it. How about, here's one that's pretty good. 4 raised to the x squared equals 2x. Oh, see, I keep writing this wrong. Not being careful. It's not 2x. 2 to the x. So, easiest and best way to solve this is try and have the same base. I got a 4 and a 2, so right now it's not the same base, but then of course you realize 4 is 2 squared. So if I do this, 2 squared raised to the x squared power is 2x. Then exponent rules are, I can multiply these, right? So it becomes 2 to the 2x squared equals 2x. And now that I do have the same base, 2x squared equals x. So how would I solve this for x? Well, this is like a quadratic equation, so let's move everything to one side. In this case, I'm going to factor out the x. It's actually going to be two solutions. For this first x, a solution is 0. From this x, looks like solution is 1/2. So there's your solutions. If you want to take the time, you could plug 0 back in for x, confirm it, plug 1/2 in and confirm that. So let's go look at one more, just because I need to do one of these, although it's not very hard, but when you first look at it, sometimes students get sort of spooked. And that is, okay, here we go, e to the x. When people see this e, sometimes they get worried, start to break out in a cold sweat. But just remember, e is just a number. It's a special number, but still just a number. Matter of fact, these are two exponential functions. I'm trying to solve for x. First thing I'm going to try and do is see if I have the same base, and if I can solve it that way. And actually I do. The base is e here, the base is e here. I just have to solve that equation. Very straightforward. Okay, now let me give you a problem that I saw in the homework. Normally I wouldn't do this, but because it was in the homework, let me give you an example of one, so maybe you won't get too stuck. The problem is if 4 to the x equals 7, then 4 to the negative 2x equals what? What we're going to do in a sense, we're going to just do some math where what I really want, I'm starting with 4 to the x. I want to do whatever I have to do to the 4 to the x, and I want to get it, change it, until it becomes 4 to the negative 2x. Now, of course, whatever I have to do to change 4 to the x into 4 to the negative 2x, I have to do the same thing to both sides of this equation. So whatever I do on the left-hand side, I have to do the same thing on the right-hand side. Because then once I do that, then I will have solved this problem. So let's see, what's the first step? Well, let's try and get a 2 in front of my x. Exponent rules say if I take 4 to the x and square it, what I do with these exponents, I multiply them. So it comes 4 to the 2x. So of course, I squared this side So I have to square this side. So I have 4 to the 2x equals 49, but if I look up here, what I really want is 4 to the negative 2x. You know what I can do? I can raise the whole left-hand side to the negative 1 power. I can do that as long as I do the same thing to both sides. You know, in the world of math, when you have an equation, you can do almost anything you want to an equation as long as you do the same thing on both sides. So here I'm going to raise both sides to the negative 1 exponent. Exponent rules are you multiply these, so this is 4 to the negative 2x. This is 49 to the negative first, which if I make that no. Yeah, I can do that. That's fine. Because now, look what I've done. I've converted 4 to the x into 4 to the negative 2x, which is what I want. And what does it equal? 1 over 49. So that's how you do that problem. You take what you're originally given, you do what you have to do to make it equal what you want, but you have to do the same thing to both sides, and then you see what happens to the other side. All right, let me give you 1 or 2 story problems, and then we're done. So now here are some problems that involve exponential functions. And once you realize it's not that hard, the reason why is these story problems, they almost always give you the equation. Usually story problems can be hard when you have to figure out the equation. In this case, they give us the equation. So let me put this on here, and I'll try and make it large enough. I found this in a book. This is like one of these nature science experiments. Number 37. It's called elk population. It says 100 elk, each 1 year old, are introduced into a game preserve. The number N of t, so big N is number of elk, t looks like it's time. The number alive after t years is predicted to be N of t equals 100 times 0.9t. So it's almost like the scientists have come in and they try to observe nature and see how things happen, and they've come up with an equation that they are going to try and estimate how many elk are living after a certain amount of time. So it's almost like now they're going to do an experiment, so they have 100 elk in this game preserve, and they're going to try, and here's the first question. Estimate the number of live after 5 years. So basically, they're going to go in and plug 5 in for t in this equation, and then this calculation will be the number of elk alive after 5 years. Pretty straightforward. So let's just write this out. So here's my equation for the number of elk. So N is number of elk. T is time in years. Now, first of all, just out of interest, now that we've been talking about exponential equations, is this kind of problem, does this represent an exponential growth kind of function or an exponential decay? In other words, as time gets bigger, is this thing growing or is it shrinking? Well, what's the key? You look at the base of your exponential function. In this case, this is 0.9, and what's the dividing line between decay and growth? The dividing line is 1, and this is on the low side. So this is actually the kind of problem that we have decay. Which sort of makes sense, right? Because the idea is in nature, some of these animals die and things happen. So if you start with 100, after a while you're not going to have 100 anymore. Another thing, just to show you what happens when t is 0. And what's going on when t is 0? Well, when t is 0, it's like the start time. It's when, you know, the timer is 0. So what happens when you plug in 0 into our equation? What's 0.9? The number of elk when the time is 0, plug in 0 for t, 100 times 0.9 to the 0. What's 0.9 to the 0 equal? Anything raised to a 0 exponent's 1. So this says at time 0, 100 elk, which makes sense. Because they're saying they put 100 elk into the park. Sometimes this number here, the coefficient in front of the exponent, is called the initial value. Because whenever the time is 0, the whole exponent goes to 1, and you're just left with the coefficient. Anyways, back to our problem. They want to know how many elk are left after 5 years. So, n of 5, here's my equation. 100, 0.9 to the 5th. This is where, in order to get this answer, you have to go grab and use your calculator. So just do order of operations, the exponents first. So I grab my calculator, I put in 0.9, then I raise it to the 5th power. That looks like it's 0.590. Then I'm going to take that times 100. Looks like there are 59 elk. The actual number is 59.049, but I rounded it to 59 elk. All right, so that is a decay problem. We began with 100, we're down to 59. So the number is decaying, the number is dropping. Not too bad. Let's do one more. Let's just do the next one. No. That's almost the same kind of problem. Let me see if I can find one more, maybe good story problem. If I can't, then this problem's a little more wordy, but let's just at least talk about it. 39, bacterial growth. The number of bacteria in a certain culture increased from 600 to 800 between 7 a.m. and 9 a.m. Assuming growth is exponential, the number F50 of bacteria TR is given by. So the key thing is all those words to come up with all those words tell you this, where F is the number of bacteria and T is the time in hours. And then the point of the problem is, all they do is they have you plug in various times and see what the bacteria is. Now the key is, I'm asking you, is the bacteria growing or decreasing? In other words, is this an exponential growth problem or exponential decay problem? The key is, what is the base of your exponential function? It's 3. Remember, the dividing line between decay problems and growth problems is 1. Since this is 3, this is a growth problem. The number of bacteria is growing as time goes on. So just for fun, if they had said, so what's the amount of bacteria after 2 hours, you would just plug in 2 for T, 600 times 3, 1800. Whoops, sorry. And then I could plug in like after 5 hours, and it's just not very hard. So hopefully if you have a few story problems with exponential functions, you'll not get worried, but realize they're actually usually not that hard. All right, so this wraps up our talks on exponential and even natural exponential functions. The next thing we're going to do is to introduce you to logs and start working with logs and logarithms. And that'll pretty much be the last topic for this math class. So, all right.